Se organiza cada vez que tenemos un expositor muy sobresaliente. Tenemos esta ocasión al doctor Gabor Herman. Lo invitó el doctor Garduño. El doctor Herman fue su supervisor de tesis. Si quieren saber algo de su historia de estudiante, pregúntenle al doctor Herman después. El doctor Herman es un matemático aplicado, pionero en la tomografía computarizada, con trabajos seminales en varios aspectos del campo. Además de sus contribuciones al campo de tomografía computarizada, el doctor Herman ha realizado importantes contribuciones a los campos de geometría digital, topología digital, tomografía discreta y procesamiento de imágenes, tanto en aspectos teóricos como en aplicaciones. Ha publicado decenas de artículos con alrededor de 40, con más de 100 citas y varios libros de texto que son obligatorios en el área. Le damos la bienvenida. Muchas gracias, doctor Herman.
The topic of today is non-ascending vectors for Shearlets, which is something that we're using in computed tomography. So, in computerized tomography, or CT, one uses optimization approaches. And the way that is introduced is that one defines the problem using a function which has two terms. One of the terms measures the lack of consistency with the observed data, which is obtained by detecting attenuation of X-rays. And the other term is a regularizing term, which measures lack of consistency with some prior knowledge. Now, one commonly investigated regularizing function is total variation. And another more recently introduced thing is to use a multi-scale geometric transform in the definition of the regularizing term. And the particular recent choice is the L1 norm of the Shearlet transform. Now, I will not actually define what the Shearlet transform is, but it's one of the huge family of transforms which is extremely popular in the last decade or so. Wavelets, curvelets, linelets, all kinds of lets. These are Shearlets. And the main thing is that the idea is that if you take the Shearlet transform of an image, which is, say, noisy, and you get rid of the terms of the Shearlet transform which have a small coefficient, you probably retain all the important information in the image, but you get rid of the noise. Using the L1 norm of the Shearlet transform as a regularizing term is a reasonably good thing to do. Now, the other topic that comes to this talk is the idea of superiorization. Superiorization is a kind of alternative to optimization. Here is optimization and here is superiorization. Superiorization is somewhat heuristic concept. Optimization is well-established mathematics. And all kinds of theorems can be proved, and mathematically interesting questions can be posed and solved. Very often, from a practical point of view, if you really just want to use these things, you don't really need to optimize the function because of several things, one of which is that, generally speaking, the mathematical function that you say you want to optimize doesn't exactly describe what you want to do for the application. So it sort of captures some aspect of it, but it's not that important that you get the minimum. Getting near the minimum is good enough. And superization is a heuristic approach which will give you something which is good enough. And the idea is the following. You usually have the primary criterion, which says how near are you to the measurements you have taken. Right? You would like to produce an image which is consistent with the measurements. And so the primary criterion usually measures consistency with the observed measurements. And typically, in mathematics, working with the primary criterion translates into a feasibility problem rather than an optimization problem. You just want to get an image which is near enough to the measurements. And typically, a feasibility problem is much easier to solve than an optimization problem. Usually there are very efficient algorithms in computed tomography which will give you a feasible image, an image which is consistent with the measurements within an epsilon. And the idea of superization, if you have an iterative algorithm to produce a feasible image, superization is a general approach which will turn that iterative algorithm into one which will give you an image which is as good as the original algorithm from the point of view of being consistent with the measurements, but in addition, it will also be good from a point of view of a secondary criterion, such as total variation or the L1 norm of the Shearlet transform. And the beauty of this is that this methodology is automatic. Like a machine, you throw into it the feasible algorithm, the algorithm which gives you the feasible answer, you throw into it the function which is your secondary criterion, and this machine will give you a new algorithm which will give you the superized version. So one nice thing about this is that when you have a new problem, when you change your secondary criterion, you don't have to rethink the whole optimization procedure. No, I have a new optimization problem. Well, I don't care. I only want to superize. I just throw it into this general procedure and I will get my answer. Now, in the process, as you will see, we will make use of the notion of a non-ascending vector D of the secondary criterion phi at the point x. And the important property is that you're at the point x. If you move away from x into the direction of the non-ascending vector, then phi will get not bigger, non-ascending rather than descending, not bigger, than what it was at x for all sufficiently small lambda. And finding a non-ascending vector is at the heart of doing superization. And so I will present some recent and to me somewhat surprising results on the practical consequences of alternative algorithms for obtaining non-ascending vectors for the L1 norm of the Shearlet transform. Okay, so to move back, what is the CT reconstruction problem? I will talk about it only in 2 dimensions, although modern CT scanners really work in 3 or even 4 dimensions when you include time. But in 2 dimensions, what you have a function f defined over the Euclidean plane, and you take line integrals of f for various lines. And the lines are parameterized by an angle of rotation relative to the coordinate system and by a distance from the origin. Every line is uniquely describable by a pair like this. And the Radon transform of the function f for t and theta is defined as the line integral of f along that line. This transform was published in a paper by Johann Radon in 1917, and he's even provided a mathematical formula for its inverse. What a CT scanner, a computed tomography scanner, does, it provides us with estimates of RF, T, theta for a finite collection of pairs. So here in pure mathematics, the Radon transform is defined as a function from one two-dimensional domain into another two-dimensional domain. But in practice, we only sample this function, the Radon transform, at a finite number of points, and that collection is referred to as the projection data. Additional problems is that you cannot, I believe, design any physical device which will give you the exact line integral, so you will only get approximations. And so we don't even have these finite samples, we only have approximations of the values of the Radon transform with finitely many points. And we wish to recover the f, which would be the X-ray attenuation coefficient, physically speaking. And another way of saying this, we wish to reconstruct a function f from noisy and incomplete set of its line integrals. One general approach to do this is referred to as a class of series expansion methods. One way of one specific kind of series expansion method, f has a physical meaning. For example, f would be supposed to be a cross-section of my body. So we know that the function that we're reconstructing is of bonded support, and we can easily estimate the support. So one way is we take the support of the function and we subdivide it into small squares referred to as pixels, picture elements, and we assume that within each one of these pixels the value of the function is uniform. So that corresponds to having a digitized image. And we use x sub j to denote the value within the jth pixel. Now, if you take r sub ij to be the length of intersection of the ith line with the jth pixel, and that we know exactly, right? Because that is just calculating for a line which I know where it is, and the intersection of it in the square where I know what it is. So the r sub ij are known. The xj is the unknown value to be assigned to the jth pixel, and this linear combination of the unknown xj should be approximately the measurement I have taken for that line. So what we have is a system of approximate linear equations, which in principle is kind of trivial to solve. In practice, it can be very difficult because the number of equations can be in the tens of millions. One has to worry about it, how to do it in practice within a reasonable time and accurately. So an alternative notation in matrix notation is that you have the vector of measurements, you have the vector of the pixel values, and you have a matrix R, which is a system matrix showing the relation between the two. And if you just want to satisfy this approximate equality and want to make it more precise, for any non-negative real number epsilon, we say that X is epsilon compatible with the measurement vector for the system matrix if the square norm of the difference between Y and Rx is less than or equal to epsilon. And here you see now the feasibility problem. I've taken a measurement Y, I know what the system matrix is, I decide what epsilon is good enough for my purposes, and now I'm trying to find an X which is within this feasible region. Now, such an epsilon compatible solution is not necessarily a good one, even if the epsilon is small, since it does not take into consideration any prior knowledge about the nature of the object that is being imaged. And that's really throwing away lots of potentially useful information. And one approach to overcoming the problem is to bring in a secondary criterion, phi, such that phi x measures the prior undesirability of x. I show you something, an X, which is an image, and you look at it and you say, I don't like this image at all because it's full of salt and pepper noise. I cannot see anything in it. If you bring in the secondary criterion, then you can set up the optimization problem. This is a feasible region, and now I say find an X star which minimizes phi subject to this being in the feasible region. And in this talk, I will mention TV and the L1 norm of the Shearlets transform as possible choices for the function phi. And here are the definitions. Total variation is a discrete approximation to the idea of the integral of the size of the gradient. You have a function of two variables and you integrate the norm of the gradient. That is the continuous mathematical definition of total variation. In the discrete definition, since we're dealing with images, you take the set of indices of pixels which are not in the rightmost column or the bottom row. So this C is the set of all the pixel locations which are not on the right edge and not at the bottom, and let Rj denote and Bj denote the pixel to the right of the jth pixel and the pixel below the jth pixel. And then the total variation is defined as the summing over all the pixels except the ones in the rightmost column and bottom row of the square root of the square of difference of the pixel value and the pixel value to its right, and the square of difference of the pixel value and the pixel value below. So this is approximately a gradient at of the image. So a discrete approximation of the continuous idea of total variation. The Herman normal Shearlets transform would take a long time to explain, but the only thing which really matters for the point of view of my talk is that it can be determined by an I by J matrix S. J is the number of pixels, I is the number of measurements. So there's a size of measurement, size of pixels, matrix S, and S of X is the discrete Shearlets transform of S. Of course, if I want to tell you what exactly it is, I have to tell you how to produce S. But from the point of view of what I'm going to do, it's not going to matter. And then the L1 norm of the Shearlets transform is, of course, you take the one norm of each of the pixel coefficients, Shearlet coefficients. So S of x is an I-dimensional vector. At any place, its value is S sub ij xj, and I take the norm of it, because this could be positive, negative, or zero. I take the norm of it, and I sum it over all the measurements. So this is the L1 norm of the Shearlet transform. Okay, so let's talk about, I claim that it's easy to produce an algorithm for feasibility. So let me just tell you about such an algorithm. This one is called the algebraic reconstruction technique, or ART. And ART is an iterative procedure. And in each iteration, we have an input vector, which is my current image, and an output vector, which is my image after the iterative step. And within the iterative step, we go through all the measurements one by one. This for an L by J matrix. And so what I do, I start with x, I set x prime to x at the beginning, then I go through one by one all the values of L, and for each value of L, I change my current estimate in this fashion. Now, here, this rho, which is one of the parameters of the procedure, is called the relaxation parameter. If you take the relaxation parameter to be 1, then when I do this step, it's exactly equal to satisfying just the Lth equation. This is a projection onto the hyperplane determined by the Lth equation, and then I go to the next equation. But typically one doesn't use rho equal to 1 because the data are noisy, so we don't want to satisfy the equations exactly, but we just choose a value between 0 and 2. And there's a mathematical theorem that if you choose rho to be strictly between 0 and 2, then repeating this procedure again and again, you will get from any point arbitrarily near to a solution if there is one. And therefore, if you stop the process when you get within epsilon, then in a finite number of steps, you get an epsilon compatible solution. So this was a feasibility approach. So how does the superization work? A general method for turning an iterative algorithm into a superization is written up, in my opinion, it's written up in a number of places, but this is my favorite, in a paper in medical physics. And what I'm going to show you is exactly the algorithm presented in the paper. And so I'm now going to talk about the superized version of ART. ART is this process, repeatedly using that. Now, here is a superized version of ART. Now, note that there are two things in this which you have to pay attention to. At this stage, I will call this procedure ART. So that is what I'm superizing. If I had another feasibility algorithm, I would put that algorithm in there. This is what I said. This is a very general thing. Here I'm doing it for ART, but you could do it for any other conjugate gradients, or whatever you like. You can put it in here. And the other, as I mentioned, at some point or other, I will need to calculate a non-ascending vector. at my current place, my current estimate. And the rest of it is just the same for everything. So for different phi's, I will have to find the non-ascending vector for that phi. For different algorithm, feasibility algorithm, I have to put that in there. The rest of it is boilerplate. You do it the same way for all the different algorithms. And what you do until you reach feasibility, you keep repeating things. This is my current estimate. I get into an inner loop, which I do capital N times. It's one of the free parameters. And what I do is in the inner loop, I change where I am by moving in the direction of the non-ascending vector. And how much do I move by? I move by something like this, where alpha is a real number strictly between 0 and 1. So if I keep going round and round and round the inner loop, alpha keep increasing all the time, and therefore, L keeps increasing all the time, and therefore alpha to the L gets arbitrarily near to 0. So eventually, this beta here will get arbitrarily small. And so by the definition of a non-ascending vector, eventually in the inner loop, I will get to a z where phi z is not greater than phi xk. So I keep going around until I find such a thing where phi didn't get increased, and I'm guaranteed that I get out of this inner loop if I have a non-ascending vector. So that's is the supervised version of art. So supervisation perturbs the original process, because the original process would just go x1, x2, x3, x4, and so on. Supervisation perturbs each iterative step before I go on. So these perturbations look something like this. And as you can see, by the definition of non-ascending vector, eventually I'm going to get to
Joining the meeting.
but at least we know that there's always one, and I can look for something better. So there are some mathematical theorems which appeared in this paper that I mentioned before, but roughly stated, the results there imply that if the epsilon is large enough to ensure that art will always find an epsilon compatible vector, that is, that the feasibility problem will be solved by the original algorithm, then the supervised version will also find an epsilon compatible vector. and this depend on being able to find a non-ascending vector. So in the same paper, here is a general theorem for finding non-ascending vectors. This is a sufficient theorem. There are other ways of finding non-ascending vectors, but this is one of them. Suppose that the phi, your secondary function, is a convex function, and suppose that we are in a j-dimensional vector space. Now I produce a function g in that vector space, which has a property that whenever the jth component of g is not zero. Now note, this is important. If the jth component of g is zero, I don't have to worry about that. The rest of the theorem is only for those components which are not zero. If the jth component is not zero, then the partial derivative of phi at x for xj exists, and its value is the jth component of g. So if the jth components are not zero, then I know the partial derivative of phi for that component. I don't say anything about the partial derivatives of phi for components where g is zero. They may not even exist. Some of the partial derivatives may not even exist. But once you have produced such a g, then we can define d, which is my intended non-ascending vector, to be the zero vector if g is the zero vector, and minus g divided by the norm of g otherwise. So it's a sort of something like the negative gradient, except that I made my life simpler because I'm not worried there are places where g is zero. So this is a theorem for producing non-ascending vectors. So now suppose that I want to find a non-ascending vector for the Shearlet transform. So let's go back to the definition of the Shearlet transform. This was the Shearlet transform. What I need to do, roughly speaking, is find partial derivatives of this thing with respect to various components. And of course, that's a problem, because if this term here is zero, then the partial derivative doesn't exist, because this is the absolute value. Whenever the thing is inside is greater than zero, then the absolute value is the same as what is inside. When the thing inside is negative, the absolute value is the minus of that. And when the thing inside is zero, then it's zero. But it's the partial derivative is not continuous and may not even be defined. But due to that part of the theorem that we don't have to worry when Gj is zero, I can make this definition, the wrong direction here. Oh, keep going in the wrong direction. Here. And this is the algorithm. I don't really want to get into the proof of that. The A sub I is a component of the Shearlet transform. And if A sub I is positive, then the partial derivative of the absolute value there is 1 for the absolute value. And if the absolute value function will have partial derivative minus 1 if what is in there is negative. So if the A sub I is greater than some theta, then I set the Z sub I to +1, otherwise I set it to -1. And if A sub I is less than theta, that's problematic. In practice, it's problematic because I'm going to obtain these things from practice. only approximately. Nothing is very precise. So I really want to avoid the zero. I don't want to be anywhere near the zero to be sure that mathematically it works. But that's all right. I can do that because what I can do, if a particular component of the Shearlet transform is less than some small number theta, then I can set G equal to 0. And then that doesn't mess up the theorem. But if it's not less than or equal to theta, then it's either greater than theta or less than minus theta. And according to it, I set Z sub I to 1 and minus 1. And then if I take if I multiply the transpose of the Shearlet transform, if I multiply that C by the transpose of the Shearlet transform, I will get exactly a G, which has the property satisfying the theorem. So this is a mathematically guaranteed algorithm for finding a non-ascending vector, and it goes further than that because I'm really a computer scientist more than a mathematician and worry about things like numerical errors. It's even guaranteed under problems of limited accuracy of the computational procedure. I just make theta large enough to avoid all numerical problems. So this is a way of finding a non-ascending vector for the Shearlet transform. So here now I show you some results. Here is a mathematically defined image. It's a 485 by 485 digitization of a mathematically described phantom object, and we simulated a computed tomography scanner. The exact size of the geometry of the scanner doesn't matter. We calculated the line integrals, and we calculated projection data. And now we try to reconstruct from the projection data. There's a classical method referred to as filtered back projection, FBP. There's the algebraic reconstruction technique, which I described for you earlier on. We can superize art using total variation, or we can superize art using Shearlet. And so what I did is I used this classical technique and reconstructed with it. And then I selected the epsilon to be the residual of the reconstruction by this technique. And I made that to be the primary criterion for the iterative procedure. So I want the iterative procedure to be at least as good as filtered back projection by the primary criterion. And here are the numerical results for different number of angles. Angles are for how many values of the theta I use for collecting the data. The things that I'm reporting on is the value of the primary criterion and the value of the two secondary criteria. This is the value of the TV, and this is the value of the L1 norm of the Shearlet transform. And these are the outputs. Now, for when I superize for TV, I would expect that the value of the TV should be less than using the other methods. And so it is. And if I superize for the L1 norm of the Shearlet transform, I would like to have the value of the L1 norm of the Shearlet transform to be less than by the other techniques, which is so for the unsupervised art and for the FBP. But in fact, if I use the supervised algorithm for TV, it actually gives me a smaller L1 norm of the Shearlet transform. So something is not working out exactly as we would have liked it to do, work out, and in fact, this is same for any one of this number of projections. So this is, if I may call it a puzzlement, for those of you who know the musical King and I, the King of Siam talks about this is a puzzlement. Well, this is a puzzlement. Why are the values of the L1 norm of the Shearlet transform higher when we superize art for that criterion than what they are for the output of the TV superization? Well, it turns out that the reason is that that inner loop where we keep pushing in the direction of making phi smaller and smaller and smaller wasn't large enough. We only went around it 10 times. And if you go around 40 times, do the superization step between the feasibility steps more often, then everything works out as it should. The L1 norm of the Shearlet transform, if you're superizing for that, is smaller than it is for TV. So that's one way of solving the puzzlement. Of course, it means that's an expensive way, because that means that you have to go 40 times, run that inner loop for each one of the feasible steps. So there was a question of why would this be? And one thing is that maybe we are too harsh here. We're too ready to even though the mathematics says we can set any component of G to 0 without doing any harm to the theory, but we're doing harm to the practice. Because when we set a component of G to 0, then we're not moving in that direction. So maybe we shouldn't be so ready to set things to 0, even though the mathematics says that it will still work out eventually, as it does. With 40 iterations, works out. So, we looked into using another way of getting the non-ascending vector for Shearlet, and this is it. We're still using a theta to avoid numerical difficulties, but we are not setting the whole of G to 0 if we hit a difficulty. We're only setting that component of Z to 0 where things are small. So this is essentially saying that whenever a component of Shearlet transform is smaller than theta, we set Zi to 0. If it's greater than 0, then we set Zi to 1. If it's less than minus theta, then we set Zi to minus 1. And that is the thing that we apply the transpose of S2. And in fact, this G also satisfies the theorem. So this is an alternative way of obtaining non-ascending vectors. And it seems to us it will avoid this difficulty of too slow motion. Let me show you another experiment which is not in CT, not computed tomography, but in positron emission tomography, for PET. This is a phantom for positron emission tomography. I won't get into the description of the PET scanner. Oops. But here, the constrained optimization problem is different from that of CT. In CT, the primary criterion was that the two norm of the difference between the measurement and the calculated measurements are within the true norm of that difference is less than epsilon. In positron emission tomography, the distance comes from statistics, and therefore the true norm between the two sides does not reflect the statistics of the machine. But there is an alternate distance measure, much beloved by statisticians, the Kuhlbach-Leiber distance. And instead of having the true norm, square true norm to be less than or equal to epsilon, I want to have the Kuhlbach-Leiber distance between the measurement and Rx to be less than or equal to epsilon. So this comes from the physics of emission tomography as opposed to CT. And the phi is the secondary criterion. So what about if we choose phi to be the L1 norm of the Shearlet transform? So, as I told you, the superization, a general procedure. All I did here to add the superized version of an algorithm called maximum likelihood expectation maximization. What is the maximum likelihood expectation maximization? It's an algorithm that has been published, an iterative algorithm, which guarantees you to get within epsilon distance, the Kuhlbach-Leiber distance. So this replaces the R step. This is the feasibility procedure. The termination criterion is when the feasibility becomes less than or equal to epsilon, and the non-ascending vector is still the non-ascending vector. The rest of the algorithm is exactly the same. A totally different application, totally different statistics, physics, and nevertheless, this just applies just as you would have had. Now, here comes the thing which I considered somewhat interesting. This is a very new result, I would say less than a month old. We started doing experiments with this, and the people who were doing it, a couple of graduate students, observed that there's some interesting behavior depending on how you set the theta. Originally, the theta was there only to avoid numerical difficulties, so I would set the theta to something like 10 to the minus 15. Okay, that should be good enough to avoid numerical difficulties. But these guys, you know, they got time on their hands, so they tried out other things as well. And this is something they reported on. The influence on theta on the L1 norm of the Shearlet transform when we stop. And they looked at both the first way of obtaining the non-ascending vector, that's the version 1, and the second way of obtaining the non-ascending vector, that is version 2. And this n is the number of times you go around the inner loop. So 8 times, 16 times, and 32 times. Those are the things they reported on. And then what is the result here is what is the resulting L1 norm of the Shearlet transform when the algorithm stops, right? The algorithm stops because eventually I satisfy this, and then the algorithm stops. So when the algorithm stops, I have the L1 norm of the Shearlet transform, and that is the thing that I'm trying to make small. And lo, the behavior of version 1 and version 2 are quite different. These 3 are for the different values of n using version 1, and it's very small theta is the best, and as you increase theta, it gets worse, and eventually it seems to settle down. So here theta is 10 to the minus 10. On the other hand, when you use version 2, for small values of theta, you have stable behavior, but quite magically, when theta gets to be as large as 10 to the minus 3, the output at the end of the termination it has a smaller L1 normal to Shearlet transform. Quite substantial improvement, as you can see here. So magically, this version 2 gives you better result, but better results for much larger theta. I must say that I haven't quite figured out what mathematical theorem implies that I should be getting this. I'm getting this. We had many experiments. I'm no doubt about that this is correct. I don't yet have an explanation. As I told you, I brought theta into this whole thing just to avoid numerical difficulties. We've way past worrying about numerical difficulties here. These thetas are pretty large, 10 to the minus 3. So that's something to look at in the near future. Oh, these are some reconstructions. This is version 1 with theta equals 10 to minus 20 when n equals 8 and n equals 32. This is version 2 with theta 10 to minus 3 with n equals 8 and n equals 32. My opinion, much nicer. This version 1, this version 2. Okay, so that's it. Using the L1 norm of the Shearlet transform at the time of algorithm termination as the figure of merit, version 2 for calculating non-ascending vectors for Shearlets leads to superior versions to version 1, and the recommended values for n and theta are 16 and 10 to minus 3 respectively. These are quite different from the recommended values for version 1, which are using n something greater than 32 and 10 to the minus 2 for theta. This is what I've been using until about 2 months ago. And then thanks to these graduate students, we came to the idea that maybe theta could be chosen differently, and we got that. So I think we're going to change our way. I think this is the end of it. Thank you for your attention.
Tenemos tiempo para un par de preguntas. Preguntas, por favor, ¿alguien? ¿No? Una de Caleb.
Hi. The superiorization algorithm that you showed, it would seem that the two conditions, it would seem they will be the error between the measurements and the estimation, plus this other two, either the total variation and or the Shearlet transform. It would seem, though, that in one of the tables, even though the other two conditions were superior, the first condition, which is the error, did go up a little bit. In both of your n equals 4 and n equals 40, I'm sorry, n equals 10 or n equals 40, whichever those two, in those two, it would seem that when you're superiorizing the three, or for example, when you're superiorizing art and using L1, in the L1 form, it did go up a little bit in comparison with art. Using 180 angles.
Let me see that I understand you correctly.
Yes.
You're saying that the primary criterion, whenever we stop, the primary criterion seems to have the same value for the different algorithms?
No, my worry here, or the basis of my question is that the primary condition did go up a little bit in comparison to, for example, art, in say 180 angles, using the primary condition in art is 3.60, while it did go up, is 3.60, or you can use that one too, the 721, for example, the primary condition is 5.37, while superiorizing art in the L1, it went up to 5.77. My question here is that obviously those two are still quite acceptable. Those are reasonable results. But still, it did went up a little bit. My question here is, what will be that acceptable norm? It will seem that giving this at least a little bit of condition to the second condition, while sacrificing even though a little bit, that's the primary condition. What will be the rule of thumb there to say how much do we sacrifice for the second condition?
Well, okay, it depends on the application. If this phantom has been designed to test how good the algorithms are for seeing small tumors in the brain. So these little white discs are the mathematical simulations of small tumors. This is the skull, these are the ventricular cavities, this is a very large tumor, these are two largest tumors, and then the tiny, tiny little tumors all over the place. And here we really are interested in those little tumors. You know, all the methods are good enough to see everything else. And if your feasibility condition is, if your epsilon is too large, then the chances are you will not see any of the small tumors. So you must make epsilon small enough that you have a chance of seeing the small tumors. On the other hand, if you make the epsilon very small, then you start putting the noise in the measurements into the reconstruction, because you want to satisfy these noisy measurements, and the only way you can do that is by making very specific changes to the reconstruction to match the noise. And then you will not see the small tumors for another reason. They will be there, but there's so much noise that they will not be visible in the noise. So that is in that application. Now in the positron emission tomography application, the story is quite different. These features here, they are not tumors. They correspond to physiological parts of the brain. All these things have Latin names. And the question is, in positron emission tomography, you inject into the body some radiopharmaceutical which will accumulate in some part of the brain if there is some dysfunction there. So the question is, what is the total activity, say, in this region, which is quite different from being able to see small tumors. So so this, in practice, how you would integrate in the reconstruction over this region, and that would tell you the total activity in this